Hello everyone, just after scraping the surface of these physical interpretations of the Schrödinger equation, okay, we want to go deeper to see really when these solutions are practical and when we can use the solutions to represent a particle in the quantum world, right? So today's lesson is about this thing called wave packets. Now you don't know what they are, but we need to talk briefly about it because it is used to handle one of the problems, the free particle problem. So for time-independent potentials, alright, the solutions are given by this over here, okay? About 2 lessons ago we talked about it, where this is the solution, this wave function is the solution of the time-independent Schrödinger equation, and we multiply that by the time evolution operator. Now there's a special name for this solution, alright? So capital psi, okay, x in terms of t, and there's a special name. This particle solution is called a stationary state. Now what's it called stationary state? Because the probability density is stationary. It does not evolve with time. Okay, so again, what's the probability density? We can take the probability density of the function to tell us about the particle, the physical meaning of where the particle is. Magnitude square that. Okay, so if we write this over here, we know about this number. The magnitude is always 1, so it's basically equals to 1, and then so we're left with this. Now this, as you can see, is time dependent. Now if you want to test your algebra a bit, or linear algebra, we also say that the probability density is given by this thing right here, right? Capital psi star multiplied by psi. So if we take psi star, we will get the conjugate of that. So we basically get this, okay, and then we multiply that by IET divided by h bar, and we multiply that by same thing, phi x and e minus IET h bar, and these two equals to 1, and we get the same thing over here. Now, more general case, based on the theory of superposition, many of you should know, we can actually superimpose various solutions, alright? Multiply them by a certain constant, and they would also be the solution to the Schrödinger equation. So really, this is also a solution to the Schrödinger equation. So we are still allowed to take, basically superimpose the solutions, multiply them by a constant, and add them up. Okay, but this is given, the constant Cn is given by this expression over here, which many of you may not know, but basically what we're doing is that we are taking the component, the n component of this function, okay, and integrate them throughout the space dimension, okay, the space dimension to get the coefficient, alright? And then later that, when we take the component, we multiply that by the function itself, the wave function psi n, take the component, multiply that by the function itself. So this is really how we superimpose solutions, okay, which still will be a solution to the Schrödinger equation. So now, we reach this point about wave packets versus stationary states. We already know what the stationaries are, the particle solution to the time-independent Schrödinger equation. What's this thing called wave packets? Now, to understand this thing called wave packets, we need to go back to the problem of consolidating classical physics and quantum physics, okay, which is again not easy. So, we talked about classical physics. Classical physics is always well localized. Okay, we always use an example of a certain body we see in a classical sense. Okay, it's always given by this position over here. It is always there. There is no strange way about it, right? But in quantum mechanics, it is that's not the case. Okay, we again talked about examples about a particle is not there until we take a measurement. So it's always moving in a certain space until we take a measurement, and that is obviously given by the probability density. Okay, so really we need an entity that really embodies these two properties. We need an entity to embody these both properties of the classical physics and quantum mechanics, because as we know, we've read a lot about articles that particles really exhibit both particle behavior and wave-like behavior. So obviously we need an entity which is somewhat like a wave function to represent the two. Now, the solutions to the Schrödinger equation is a step towards that. It is progress towards that, but it's not entirely the case, alright? Why do I say that? Because now, for this solution, okay, which we know is again a bound solution, it is fine. This bound solution is fine. We can normalize it, so really, we know that we can find the probability over here, and since the probability when we sum them up is equals to 1, okay, it's actually the probability of finding the particle over there. But the problem lies when we have something called an unbound solution, remember? That's why we're always going back to this bound states and unbound states. When we have an unbound solution, or a bound state if it's for all energy values, we cannot normalize it. You can see, as we integrate from minus infinity to infinity of the probability density function, okay, we will get infinity, infinite area. So we can't normalize it. So how do we use this wave function to really represent the particle, okay, and the position of the particle? We need to kind of develop this method where we can really use this wave function. Okay, now that's why there's a method to do that, and since we understand the problem, okay, we are going to springboard from the idea of the superposition to find a way around this problem, right? So we've solved the time-independent Schrödinger equation. We get an about solution. How are we going to use that to represent the particle? Okay, that is by using this superposition principle over here. Now, this is a wave function. Am I correct? Okay. If we can somehow make the wave function, okay, confine the wave function towards a classical trajectory. Classical trajectory, okay? So we got a certain particle, and the classical trajectory, let's just say, is within here and within here, okay? So if we can somehow confine this wave function in this classical trajectory and make it vanish, okay, at all spaces, so basically the wave function is 0 at the spaces over here, we will, get a wave function something like a bound state. Now, when we do this, we can normalize this wave function, okay? We can normalize the unbound states by using some sort of process to make the wave function confine this classical trajectory. That process is by taking the solutions and multiplying them with a certain amplitude so that they interfere constructively in this region but destructively somewhere else. Alright, now see, we're getting somewhere.